Good day, everyone. I would, I hope you've all subscribed and liked this YouTube channel. I'll be explaining what we call mathematical induction. Mathematical induction. Mathematical induction. So, in this episode of mathematics, I'll be talking about mathematical induction. What is mathematical induction? It is just a method of proving statements. Let's just take note of that. It is a method of proving. It's a method of proving. Is a method of proving that a statement involving natural numbers are true. Right? It's a method of proving that statements involving natural numbers are true for all the natural numbers. So mathematical induction is not a kind of hard expression to prove, right? Because mathematical induction is not hard to prove. Mathematical induction just involves you using the representation being given to you or the principle being given to you, then prove if this principle is true or not. That is just what mathematical induction is talking about. Okay, let's take a look at you know what natural numbers are. First of all, natural numbers are just basically numbers, or natural numbers involves both odd numbers and even numbers. Natural numbers involves integers, both positive integers and negative integers, right? So let's just proceed to talking about some questions. Let's say, for example, let's try some examples here. Let's take a look at example 1. Using mathematical induction, show that the following statement is true. Show that the following statement is true for all natural numbers. This is the question. But what is the statement? This is the question, but what is the statement, or where is the statement? This is the question, but where is the statement? This is not the statement. The statement is n semicolon 1 plus 3 plus 5 plus and so on plus 2n minus 1 will give us n squared. Now, to explain this expression properly, is that what it means is that when your n is equals to 1, let me explain this expression properly. When your n is equals to 1, right, and when you sum your n is equals to 1, will it also give you n equals to square, or will it give you your n square? That is, will n give you n square? That's what we are trying to bring out. Or when you add everything all together, will it still give you your n square? Okay, let's take a look at what I'm trying to say. We want to prove if it is true for all the natural numbers. Okay, let's take a look at the first one, n. When n is equals to 1, right, this expression we are looking at is this. Okay, let's take a look at n square. N square is equals to 1 raised to power 2. So 1 raised to power 2 is what? Is 1. So it means that this and this are true, right? So n is equals to n square. That is true. That is the true expression for this one. So let's take a look at when n is 2. I get it now. When n is 2, are we having it to be n squared, that's 2 raised to power 2, that is 4, right? Now take a look at this. Take a look at this. Now the expression here is talking about 1 plus 3 plus 5 plus and so on. Now it means that when I add 1 plus 3, will it give me 4? Will it really give me 4? Yes, it's. Now it means that when I add these three numbers, or these two numbers, the first two numbers, the first two natural numbers, if I add the first two odd, they are odd, these are odd natural numbers. So when I add the first two odd natural numbers, will they give me 4? Yes, 1 and 3 will give me 4, meaning n raised to power n, when n is 2, my n square is giving me the addition of these two natural odd numbers. So this is also true. Okay, let's take a look at when n is 3. When n is 3, n square will be 3 raised to power 2, that is 9, right? So if I add these three natural numbers together, these three odd natural numbers, if I add the three of them together, will they give me 9? That is what we want to find if it is true. Let's say 1 plus 3, then plus 5. Let's say 1 plus 3 is 4. 4 plus 5 is what? 9. So adding these three natural, three odd natural consecutive numbers, by the time I add them together, they gave me. So this is true. Are you getting it now? Okay, let's take a look at more forms. Right? N raised to power 4. N, when n is equals to 4, n square is what? 4 raised to power 2, that's 16. So what are our odd numbers? We have odd numbers from 1, 3, 5, 7. Do we have 7? 7. What else again? So let's take a look at the other ones. 3, 1, 3, 5, 7, 9, right? So let's take a look at it. This is 1 plus 3 plus 5 plus 7, right? So this is what we are trying to do. What we are trying to do is that what we are trying to determine, or what we are trying to prove, is that we look at the sum of the first positive odd numbers, right, as it progresses. This is 1, this is 2, this is 3, this is 4. So by the time we add the sum of the first 4 odd numbers, first 4 odd numbers, so by the time we add all of them together, will they give us 16? So let's take a look at it. 1 plus 3 is what? 4. 4 plus 5 is what? 9. 9 plus 7 is what? 16. So definitely this is also true. So it means that this statement and this expression is what? Is true for all. So it means that the statement is true for all natural, is true for all addition. It's true for all addition, or let me just put it the way they gave it to us. For all, the statement is true for all natural numbers. The statement is true because using this statement, it means it is true for all natural numbers. Okay, let's confirm. We just did 1, we did 2, we did 3, and we did 4. Let's take a look at let's take a look at first 10 numbers. Let's take a look at first 10 numbers. For first 10 numbers, we use 2n we're going to use 2n minus 1 equals to n squared. So will this work? Let's use when n is equals to when n is equals to 8. So when n is equals to 8, meaning we need the first we need sum of first odd numbers. We need sum of first eight odd numbers. And what are the first 8 odd numbers? We have 1, 3, 5, 7, 9, 11, 13, 15, 1, 2, 3, 4, 5, 6, 7, 8. So let's remove this. So this is the first 8 numbers, right? Now these are the first 8. So let's take a look at our expression. N square is 8 square. 8 square is what? 64, right? So let's take a look at the sum. 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15. 1 plus 3 is 8. So I said 8. 1 plus 3 is 4. 4 plus this is 9. 9 plus this is 16. 16 plus 9. 16 plus 9 is 25. 25 plus 11 is 36. 36 plus 13 is 49. Are you getting it now? 49 plus 13 is 49 plus 15 is 6. That's 64. So definitely this and this are true. So our statement is correctly our statement means that it is correct. So this statement given to us, right? Did I do -1? Okay, yes. This statement means that it is definitely true. It is true for all natural numbers. It is true for all natural numbers. So if we take a look at 2 times 8 minus 1, that's 2 times 16 minus 1, that's 15. That's 15. So what is this? What's this one here is trying to tell us that what this expression here that is given in this question earlier on is to tell you that our last value here, we are looking at 8 when n is 8. When n is 8, right? When n is 8, what we are trying to look at is that 2 times 8 in this expression. 2 times 8 is 16. 16 minus 1 is what? 15. So 15 is the last number here. Can you see it? 15 is the last number here. If you are trying for n equals to, or when n is let's say when n is 10. When n is 10, it means that 2n minus 1, that is 2n minus 1. When n is 10, 2n minus 1, that will be 2 times 10 minus 1, that is 20. Minus 1 is what? 19. So it means that all your odd numbers that you're going to write, the last number is going to be 19. So you are going to be going 1 plus 3, 5, 7, 8, 9, 7, 9, 11, 13, 15. After 15 is 17. After 17 is 19. So you add all these 19 together. Whatsoever answer you get is going to be the sum of the odd numbers you are going to add will end in 19. The sum of all the odd numbers you are going to add will end in 19. That is when your n is 10. Sure, you get it now. So that is just an expression to this on mathematical induction. Mathematical induction is just to prove if a statement is true or false. just to prove if it is true or false. So in the next episode, I'll talk about another question, another example on mathematical induction.